Hello everyone. Today I will talk about elliptic curves and ZK proof aggregation, which I worked on around like 1 year to implement this aggregation structure, and I wanted to share this with all the developers around the world. And yeah, it will be a little bit high level, I guess, but I wanted to keep it as low level as I can. So yeah, if you have any question, you can just ask. Feel free to ask. Yeah, I'm working for PAC team in Ethereum Foundation. It's like more like sub team. We are working on ZK and zero knowledge technologies. We are researching and implementing new algorithms. And Andy talked before me, and I think you guys already know that. You can join us from this Discord QR code, and this is my GitHub address. You can reach whenever you want to ask any question or see my implementations. So first we can start with elliptic curves. We need to understand how actually zero knowledge proofs are, how we implement or how we calculate them, and I will try to explain it a little bit, and then we can continue with this. So first of all, we have different kind of elliptic curves, and in ZK technologies, we mostly use Weierstrass form, and we are constructing these elliptic curves over our finite fields. And when we construct these elliptic curves, we need to choose some. We need to look for some, security things, so like security protocols to not reduce our soundness or zero knowledge criteria. So you can see here we have y square is equal to x cube and ax plus b. This is our general form. We will follow this to build our elliptic curve, and you can see images here that we have different kind of curves. When we choose these, we need to be careful about singularities because we don't want this. If we have singularity, cusp or node, for example, we have two different singularity types. If we have cusp, that means we have one same tangent line, which I will show you what it will mean. It doesn't help us we don't want to use this because we will have multiple results. And for node, we will have two distinct tangent line. It's also what we are trying to avoid of. And there's a formula that we need to follow, and if it's equal to 0, that means we have singularity. And as I told you, we are trying to avoid it. So as I told you, we are constructing these elliptic curves on our finite fields. That's why we need to understand these finite fields, what operations we can do with this, and how they work. For example, like I will directly say that the real numbers that we already know from mathematics are a good example of finite fields with uncountably many elements. And we have like plus and, as I show that plus and multiplication are operators. Here, finite fields on elliptic curves looks like something like this. What this finite field means over our elliptic curve is that we are using modulus as our finite fields is our modulus, and we are constructing this using this modulus to wrap up every time if we pass the numbers that we are using in our elliptic curve to keep inside a finite field. And with this way we can do many operations that's very hard to find very hard to find, for example, our private key from public key. But when we choose our finite field, we need to be careful about it to be prime number, because if it's not a prime number, we will have no solutions for some numbers. As I show here, if you have mode 4, that means your 2 times x is equal to 1 will have no solution for us. And that is also something that we are trying to avoid. And this finite field, in these examples, you can see some dots. Like on the left corner, left upper corner, you can see that we are using mode 19, and you have some results for your elliptic curve. And these results are our actually sets, actually group members. This is why we are trying to pick a big finite field or base field that increases our number of results, and it makes it hard to find the results. And yeah, like you can't calculate from your public key to your private key because we are using very big numbers here. And as you can see that if you just increase it to 487, you will have already a lot of results. And we are using 2 over 256, which is very, very big number. So yeah. This finite field, as shown here as an example, we call this as base field. This is our base field in elliptic curves. After we create our, we choose our finite field, which is base field, as I told you. We choose our base field, then we construct our elliptic curve over it, and we will have some group elements. But what's group? We need to understand this first. So group has only one operation, which is addition, and you cannot have any other operation except addition. And if you want a set to be a group, you need to follow these 5 properties to satisfy. The first one is closure. Like if A and B are members of the set, then A plus B must also be in the set. So you can't get any result that's not in your group. And the second one is associativity, and this is like A plus B in parentheses plus C should be equal, as you saw in the slide. Identity element, you should have this as well. Element 0, which if you add, it will equal to the number itself. A plus 0 is A, yeah. Or 0 plus A is A. Inverse, for every element existent Z, if you add to itself, to your original number, you should get 0. And commutativity is A plus B is equal to B plus A, as you show in identity element section, like it doesn't change any result. So these properties we should have in our sets, so we can call them as groups. So groups in elliptic curves, how they work. So as I told you that we have modulus, which is our base field that we are putting numbers and we are getting results. And when we pick this, like we are trying to have a good elliptic curve which gives us most amount of group orders, which means that we will have maximum amount of results with our base field. What does this mean? P is one of our results, for example, and Q and R, like if you want, points. And if you want to add this P and Q with mod with our using finite field, we should get a result which is on elliptic curve as well. If you cannot get any other result out from this line, because it won't work. In that case, it will just get some trash values. So yeah, this group addition, we have groups and we have just plus operation. As I told you, we need to calculate this. If we have P point and Q point, if we want to add these two, we will say, okay, we need to draw a line from P to Q, and we will intersect at a third point, and this will be our the result. So P plus Q is equal to minus R, and we are taking our inverse. Sorry, mirror image, like, yeah, inverse. Then that means you can say that P plus Q plus R is equal to 0. And R is our result. This is how we do plus operation. So, and we have double operation, which is also derives from addition, but we are using some kind of different technique. And by the way, when we calculate this P, for example, they have X coordinates and Y coordinates, as you know, and they are all in base field. I want to say this again. And we are taking Q, and if you calculate the tangent line of it, it means it will go and intersect at a point, as shown here, with, like, you are taking tangent line of Q, and it goes to P. That means we are doubling Q. Q plus Q is equal to P minus, and yeah, you can say that P plus Q is equal to 0. This is how we are doing double operation. We are using all these operations in our ZK proof calculations. That's why I'm trying to explain this. And here is a good case that if you want to add P to its inverse, you will get point at infinity. And this means that actually it's not completely 0, but in projective space, which is X, Y, Z, you will get zeros, yes, but in two-dimension world, it will be point at infinity. 0 is our point at infinity. Here as well, you can see that if your P is equal to 0, which is point at infinity, if you want to add P to P or add any other thing or double it, you will get just straight line, which is tangent line of it, and you won't get any intersection point. That's why we don't want to we don't have any results with it, and we call it like it's point at infinity. Result is point at infinity. Okay, so with these operations, if you look here, I have an example of scalar multiplication. What is the multiplication? I told you guys that we don't have any other operations except addition. But if you add P plus, if you do operation P plus P, which means we will have 2P, and if you add another P, you will have 3P and 4P, 5P. You can add all of these P's and you will get scalar numbers before your group element, which we call that they are scalar fields. And with these scalar numbers, we can use some kind of addition and doubling operation to calculate this, for example, 11P. So how we do that? 11P, we will take 11, this scalar value, and we will convert it to bits, which is 1011, and we can say that 11P is equal to this formula, which is, you can see that if it's 0, you are multiplying with it 0. If it's not, you are adding it and doubling it. I can explain it like this. So we are taking P and we are doubling it. I showed you double operation, so we will do this double operation and we will get 2P. If it's 1, 1, 0, 1, 1, in 11, you can see on the right corner we have 1. This means it's true, and we can add this double operation to main sum operation. So we are taking this 2P and adding to 0, which we have 2P right now. And, sorry, we are adding to P. And then we are doubling 2P, so we can get 4P, but in the second, I'm very sorry, in the first operation, we are getting P and we are keeping it. In the second one, we are doubling it and we are getting 2P and we are adding to our first P, we get 3P. Then we are doubling 2P to get 4P, but we have 0, which means you don't want to add it. Then we are skipping it and we are just doubling our 4P and we are getting 8P, and we are adding it to our sum, which 8 plus 3 means we get 11. So this is how we do multiplication operation in our elliptic curves. And this gives us scalar field. In elliptic curves, you can see that in zero knowledge calculations, you can see that we have two different fields. Maybe you wondered before, like what space field, what scalar field. In general, we say FQ is our scalar field, and this ability to add and double gives us these scalar values. And if it's a prime number, we can say that this is our scalar. Base field is our field that which we constructed our elliptic curve. And we call it mostly like FR in our calculations. It changes. This is our scalar field, yeah. So yeah, I can start explaining zero knowledge proofs. So we learned actually, or we saw how elliptic curve operations works and what space field was scalar field. And right now we can see what are zero knowledge proofs, then we can understand how we can aggregate them. Zero knowledge proofs are the proofs that you don't have to give any information to verifier, but you can still convince them that you have the true witnesses, which is like our values, that you can say that, okay, I know this result of this puzzle, and it's the most common topic, example, and you can say that, okay, I know this result of this puzzle, and they will say, okay, I convinced that you know this. This is basically what zero knowledge proves. But to accept them as zero knowledge proofs, we need to follow these three criteria because they are very important. Completeness is that if your input is valid, that like if you know the result of your puzzle, that means your proof will always return true. It cannot return false. There is no chance for that, so we call it as completeness. It's very important criteria, and soundness is also it's the most important, I guess. Like if the input is invalid, you can't trick someone. You can say, okay, I am confirming this one, or I have this proof that I sent money to someone, and they can say, okay, I believe it. This is not the case with zero knowledge proofs. It's very tiny margin that they can trick, but this tiny margin is very tiny that like 2 over 256 means that the probability of trick someone is like it's very tiny. Yeah, I was going to say that we have more atoms, or like we have more planets in universe and suns and black holes. Think all of them, like you need to choose the Earth with knowing all of these planets to, okay, this is the true proof. It's like impossible. It's that big. Zero knowledge means that no one learns anything, basically. It's the name. Oh, sorry. Okay, witnesses. Okay, I have a little bit. Okay, I need to be a little bit fast. Witness are our values that we don't want to share with others, which we create our zero knowledge proofs with using them. If we give our witness values, that means they know our results. It's not the case. We don't want to do this. Challenge is the verifier randomly picks a number and gives to verifier picks a random number and gives the prover and says, okay, try to use this, give me the response. And the response means that they are just passing some values and okay, at the end, it's correct. This is basically zero knowledge elements, but in snarks, we don't have these. It's another topic, I want to pass this. Okay, proof aggregation. It's the hard part, I guess. So this is basically the schema of like how we aggregate proofs. If you prove the proof at the above one, that means all the proofs under it they are all correct. Just one proof and you can verify thousands of them with just one proof. How we can do this? As I explained, field arithmetic, we are using non-native field arithmetic, which means we are using our scalar field to build constraints, and we get results on our base field. So if you get results on base field, how you can use your proofs to create a new proof? You need to carry them to our native or scalar field to construct these constraints again. So we are using non-native field arithmetic operation to construct this, and yeah, I will show you how we do this. We have Chinese remainder theorem and RNS, which is residue number system. Let me pass. Chinese remainder theorem is if you know the result of x in 5, 7, 11, you can find x value in mod 385. This is how we can keep our values tracked. And for residue number system is That means if you have smaller field, which is our scalar field, bigger field is base field, you can always have a number that that carries the same value in your base field without, colliding with another element. So this is what resident number system tells to us. I had a little bit example, but I think time's up, so I want to pass this. But yeah, this is how we do it. Thanks for listening. Yeah, if you have any questions, yeah.
Yeah, if we have a question, we can have one question maybe. Yeah, we we do have a question.
I'm surprised actually. So
Thank you. No, really interesting talk.
Thank you.
My question was, if I want to be a CK developer, should I try to learn all the inner workings about it, or just try to do like a domain-specific language or something more like abstract and high level?
If you want to be a ZK developer, yeah, I think you need to learn all of this. So I was trying to be very, high level, but yeah, you need to learn all of this because we have a lot of operations, and you need to know how these elliptic curves works actually. And yeah, I must say yes, maybe not non-native field arithmetic because it's not very common thing. I think we have like 4 or 5 implementation around the world, and that's very, odd case, but you need to learn elliptic curve because we are doing all the operations on elliptic curves. Yeah.
Thank you.
Thank you for asking.
Yeah, thank you so much, Armanc.
Yeah, thank you for listening.
Thank you so much, Armanc.